or to the cloud. And also let's start the presentation. Share the screen, which screen? Okay, the screen. Okay, so finally we came to the so far that we are going to talk about the electric drive system. So we learned many components in an electric vehicle, and now it is time to talk about the electric drive system. But I believe that many of you already have an understanding for the electric drive system, but it doesn't hurt that we repeat the basics and the trends in an electric vehicle, because it is an application and each application is going to have its own needs. So let me take it to the presentation view so I don't see it. Oh, that's great. Actually, okay. There's some problem with my computer. Okay, this is the only thing that we can see. So perfect. Now I open that. Okay, I'm not going to take it to the presentation view. I'm going to use it as it is. Okay, this can stay here. Okay, so we are going to finally talk about the electric drive system. And today I'm just going to give you an overview of the electric drive systems in an electric vehicle. And maybe now it will be too much because we are going to use so many terminology, different winding types, different rotor types, different that type, this type. But once we go into the electric machines and inverters, you are going to have a better understanding of what we are talking about. So just try to understand the terminology. I'm going to give you also some examples. So in this case, let's start by the definition of the electric traction system. Let me also take the view. I don't want to see myself. Okay, now I'm almost done. So I want to start with the definition of the electric traction system. As we learned in a hybrid electric vehicle or electric vehicle, we are going to have one way or smaller or bigger electric machine. And in most of the hybrid electric vehicles today, the electric motors are also helping for the traction assist. So therefore, the size of the electric machines are getting bigger even in a hybrid electric vehicle. And we learned many different types. So we know where to place the electric machine and what is the role of the electric machine and so on. When we talk about the electric traction system, actually we are talking about an AC machine or electric machine. Actually, this could be also a DC machine, but it is not common to use a DC machine in a high performance application. And as I'm going to talk, so almost all the machines have three-phase AC machines. So you can think that in an electric traction application, we use three-phase AC machines because of their better performance compared to DC machines. And to be able to drive an AC machine, we need to have a voltage source inverter, because as we have learned, and we talked about it for many weeks, on board we have a DC voltage available. So we need to have a DC to AC converter, which is called an inverter. And since the machines are three-phase, we also want to have, since this is usually a three-phase machine, then we also need to have a three-phase voltage source inverter. Those inverters are called voltage source because they are basically chopping the voltage, and it is very common to have the voltage source type inverters. We don't have many current source type inverters. And in this case, if we had a 5-phase machine or 7-phase machine, different number of the phases, then of course the inverter should also have so many phases. So here we have a 3-phase voltage source inverter. We have 3 legs, 1, 2, 3, because we have a 3-phase AC machine. As you can see, we have 1, 2, 3 connections. And basically this inverter plus the AC machine plus the sensors where we are going to measure the voltage and current. So this is what you will do in an electric traction system. So it is very common to measure the line currents of the machine. So this line currents. We can also measure the DC link currents. Plus, we also like to measure the DC link voltage, because this DC link voltage is going to be important for the control and to understand the state of the drive system. So this voltage is needed for the control purposes plus safety purposes. So if this voltage is getting too high, then it can be dangerous for the components. So we need to just do something if the voltage is getting super high. And this current is used for the control purposes. And we can measure, as I said, the phase currents. Sometimes two of them are enough if we don't have any faults and a symmetrical system. Moreover, the DC link voltage. We don't measure the voltages here. We will talk about it later. We just measure the DC link voltage. And on top of that, we need also speed and position information. So the position information is required for some type of machines, or it may not be required for other type of machines. But if we need it for the synchronous machines, for sure, for the synchronous machines, we need the position information. Plus, we are going to measure the temperature all over the drive system. We are going to measure the temperature of the inverter. We are going to measure the temperature of the motor, so that we make sure that our system is operating within the allowed temperature limits. So therefore, the cooling is going to be a very important part of our drive system. So as we talked on Tuesday, there is a trend of putting everything together. So the inverter, the electric machine, and the gearbox together. And actually in these systems, we also have the differential, because they are going to be placed on the X, and there will be one side going to the left wheel and the other side will be going to the right wheel. So we know that actually we need to have a gearbox plus a differential included. So here we are going to have a gearbox plus a differential so that it can be directly placed on the X. So we want to have everything super compact and also modular. So it means that if we have a system, we want to have it in different power ratings and torque ratings, and we want it to be directly connected on the electric vehicle shaft to make sure that we have a compact design. And as you know, for the power electronics, the compact design is important in terms of the stray capacitances and stray inductances. So we want to make things closer to each other. But of course, there is the limit. If you make things too close, then they will start to affect each other. So the analysis is going to be hard, and you also need to consider other factors. And the most important thing maybe in an integrated system is the cooling. So here you don't see much regarding to the cooling in the system. We will also talk more about the cooling, but maybe you just see these. These are the coolant inlets and outlets, most probably. And in the cooling should be done for the electric machine and for the inverter. But the electric machine and inverter, they have different cooling needs. So the electric machine can at least stay warm for a while, and it will take for it some time to get warm. But the inverter has to be cooled more with more care. So therefore, usually if you have the integrated drive, you want to make sure that the cooling system is designed carefully, so it will be enough for the inverter. But the cooling system is very, very important part of the things, as we will discuss later. So there are some requirements which is related to traction application. So it is not an easy application, being a mobile application, and it is a cost-driven market. So therefore, there is a need that we need to make everything smaller. If it is a mobile application, it means that you have the weight constraints and you have the volume constraints, and that will come with the requirement of high torque density and high power density. So it means that even if you need a high torque, even if you need a high power, then you want to have a compact system, because you are going to keep carrying the system in the vehicle and you need to spare space for the system. So it means that it has to be compact. So this is regarding to the need of the compact design. And we need to high torque. So what do we need from a traction system? So as we discussed earlier, we need the high torque at low speeds, and you have done it also in your projects. This high torque was required basically at low speeds for starting and for acceleration. And moreover, for the hill climbing, if you have a high slope, then you also drive at low speeds, but you need a high torque. So one of the requirements is you need the compact design and you need a high torque at low speed. So this is the speed and this is the torque. So at low speeds, you need a high torque, and this region is going to be used as for the starting and acceleration. On the other hand, at high power, you need also, at high speed, you need a high power. So basically, as we have discussed many times, so you need such a characteristic. So here is the constant torque region, and here is going to be the constant power region. So constant power, it is not going to be perfectly constant, but we can make it close to the constant. So this is going to be the constant torque region. And here is for the high speed operation, and here is for the acceleration. And moreover, the vehicles need an intermittent overload capability. It means that we need to define a short time, that's called short time characteristics, plus a continuous characteristics. So the continuous characteristics is usually long time, that's long duration, short duration characteristics. And depending on the manufacturer and the need of the vehicle, there are different definitions. But we can talk about, for example, if it is short time, most probably it is going to be in the range of, we can define 10-second characteristics, 30-second characteristics, or 60-second characteristics for the fold system. And long duration is going to be minutes. So for example, 30 minutes or 60 minutes operation. So it means that we need to have a system which can operate at a given torque speed characteristics for a very long time. For example, assume that this is some torque T continuous of the system, and this is going to be P continuous. No, this is not P. This is still T continuous of the system. And in an electric vehicle, we need to have the overload capability. So here it's going to be, the power doesn't need to increase much, but usually it does come with the torque increase. So here it is going to be T, like short duration. Let's keep the name which I write today. So this is the T of the short duration, and this will be just allowed for a shorter time. And in some manufacturers also talk about the many T's, like for 10-second torque characteristics, 30-second torque characteristics. So you can put here many different curves. But the idea behind it is, since the system has to be cooled, and our limits, one of our limits is the problem that the system is getting hot, we can allow some high torques, but for a shorter time. So if you, for example, if you have 150 Newton meters continuously, this will be enough for the regular driving. And you may need for a short time 250 Newton meters just for a short time. And as you were doing in your projects, for the acceleration, you need 10 seconds. And it is enough for you if you have this red curve just for 10 seconds for a good acceleration. Or if you want to overtake a car, it will take 10 seconds. You don't overtake a car in minutes. So, and actually, you know, if you apply a very high torque for 30 minutes, so there is not such an application. You will just go beyond your high speed limits. So it means that actually you are very familiar with that from your projects, that you need to have, it is good to have a high torque, but you don't need it for a long period. So you just need it for a short period. So based on that, we do our design accordingly. We say that we need that much torque, but for a very short time. And we can decide on the cooling system, whatever we are going to cool, based on this need. And when we talk about the steady state, it means that we need, if at this 150 Newton meters, we should be able to cool our electric motor for infinitely long time, 30 minutes, 60 minutes, and so on. And as you have seen from the projects, you are not going to operate here, at least for some of the groups. So you are always going to operate at the low torque region. This high torque region is going to be used just, as I said, for the acceleration, and high torque region at the high speed is going to be used for overtaking, not for a very long time. So this is a very important criteria. So we need to design our system based on that. Moreover, we need to have a high efficiency. High efficiency requirement is actually straightforward. We need to have a high efficiency so that we can get a long range. If we have a low efficiency, then it means that we need to put more battery. If we have more battery, the efficiency will decrease, and so on. So the high efficiency over a wide speed range is important so that we can get a long range. Moreover, it is also very important to get not the long range, but also let me say that I don't trust my computer today. And this high efficiency is also important for another reason, so that we can make the device compact design. Because if you have a low efficiency means more losses, and more losses means more cooling need, more cooling required. So actually this high efficiency is also related to the compact design. So we want to have a high efficiency in the system. And the last one is here. It looks a little hidden because of all the things that I put on the slide. Wide constant power speed range. I think we haven't defined that earlier. This CPSR, constant power speed range. So here is the constant power range. And the speed that we start, let's check it from the continuous. It may be different between the base speed can be different for the maximum torque operation, or the short duration operation, or long duration operation. Let's check it for this case. Assume that this is the base speed. We will also repeat the definition of the base speed, and this is the maximum speed. So this CPSR is defined as N max divided by N base. And if we can get it in the range of 4, actually it is a good design. So the reason why we want to get 4 or 5 is because of the fact that actually we want to have a high torque at low speeds for the acceleration, but we don't want to have this high torque for a long time. So if we have it for a while, then it will be enough. But if we want to have this curve to continue, if this can continue, this will be good because this is related to our maximum speed. So one thing that you can observe from the electric machines, electric vehicles, is the fact that many of them has a limited maximum speed. So they limit their speeds around 150 or 160 kilometers per hour, because it is not so easy to design a machine from which you can go to the high speeds by keeping the power constant. So this wide constant power speed range is also related to the compact design. Of course, you can get a wide constant power speed range if you have lots of space for the electric machine. You can just design an electric machine. But it is hard to get this, all of them at the same time. So the problem is actually this. It is maybe better to put them here. To get a compact design, to get high efficiency, and to get required characteristics characteristics. These required characteristics can be taught as high torque at low speeds and constant power at high speeds. So to get them all in once is hard. So you can get a high efficiency if you don't have a compact design. At the moment you have a compact design, it means that you are going to increase the current density, you are going to increase the B in the motor, and you also have to include some cooling. So it is going to deteriorate the high efficiency. But high efficiency is also good for the compact design. So you need to design them at the same time. Moreover, if you want to have a high torque, then you need space because you need to somehow supply the current to the system. And if you want to have a high power, it is also different from each other, because then it means that you don't want to have a high B in the system. So they are also going to be, if you want to have a high torque, usually you don't have a high constant power. If you want to have a high constant power at high speeds, then usually you won't have a torque. So these are also not easy to get at the same time if you have to make a compact design. So being a mobile application, we want to have them all at once. So we have to nicely optimize the electric machine. So I found some torque speed characteristics. So it is very common for us to just show the torque speed characteristics in the first quadrant. You can just assume that we are going to have a similar torque speed characteristics in the other quadrant, because you know that our electric motor is going to operate at, even if you are driving in the only one direction, it is going to operate in two quadrants. So here it is going to be the motoring, where the torque times speed is positive, M times N is positive. And here it is going to be the regenerative braking mode. And here going to be torque. Why I use N for the torque times speed. Actually, don't use the speed. It is not good in terms of SI units. Torque times speed is going to be less than 0 for a positive speed. So we always talk about the characteristics in the first quadrant, but you can assume that the characteristics in this quadrant, I don't know how you call it, the fourth quadrant, is going to be also the same. So when we look at these characteristics in the first quadrant, so there was a paper in IEEE, a conference paper, I got this curve from that. So they were looking in a system with maximum speed of 7,000 and maximum torque around 160 Newton meters. And actually in this paper, they try to make sure that they can get a high extended constant power range by using two motors in the front axle and the rear axle. But we just want to check the characteristics. So here you see the constant torque region, and there are two limits. The first limit is for continuous motor operation, here shown with the blue, this curve. And the second curve is the maximum torque operation. So it means that this is just allowed for a limited time, for 60 seconds, 30 seconds, depend on the definition. And then the torque power, we will enter into the constant power region. This is for the constant operation, and this is for the maximum operation, or for the short duration operation. And here they also showed that actually peak torque is required if we have a slope or we want to accelerate in this part. This peak torques are going to be required. And this continuous torque is when we have less slope, we may need this continuous slope. And for the high speed case, if we are more or less on a straight load, then this will be enough. This much power is going to be enough for the regular driving. But of course, this high power in the high speed, you may need to just climb a slope, or maybe you may need it for the acceleration, because if you want to accelerate to the maximum speed of the vehicle, you also need some excess torque, and you can also use this excess torque for the acceleration. So you can also use it for this line for overtaking the other vehicles. but you will need it just for a short time. So here, the idea is, first of all, this constant, this CP, this constant power speed range is an important criteria. So the overload capability is another criteria, because you want to design your machine for this characteristics for continuous operation, but you want it to give you maybe double performance for a short times, less than a minute cases. And also we need this high power for the cruising. So we will have such a characteristics. Of course, the machines are not going to give us the exact this characteristics. This is what we want from the machine. And if we can get some characteristics close to that, at least a little better than that, it will be fine. But these are the ideal characteristics. The machines are going to have their own characteristics. I'm going to show some characteristics later. Maybe it's time to show it too. So this BMW i3 characteristics, there are two machines, one the sport version and one the regular version. The sport version has a higher power and higher torque. The regular version has 250 Newton meters as the peak torque, and the torque starts decreasing around 4,700 RPM. In this case, it can have higher torque to 270 Newton meters, and the torque starts to decrease around 4,500 RPM. And what you can see here is actually this machine can keep the top power more or less. As the speed goes to the 12,000 RPM, the power can be kept. So as you can see here, the peak power is 135, but at the very high speed, you can still get 120 kilowatts. On the other hand, this machine can give you 125 kilowatts at the base speed, but its power keeps decreasing. Look, it cannot even reach to 12K. It stops somewhere around 11,050 RPM. And it also can give only 80 kilowatts of power. So what I have shown you, actually, it is what we want. This is what we will be very happy to have it. But it doesn't mean that all the electric machines are is capable of giving you that characteristics. It is related to the design, but if you, for example, have a better design, you can come close to those characteristics. But in other cases, if you are not designing a performance vehicle, you will be maybe okay to that the power of your system is decreasing at high speeds. But just to make sure, these are idealized characteristics. So this is what we want from the vehicle. This is not what the vehicle can give us. And on top of the requirements for the drive system, of course, here the electric machine and inverter, both of them has to give these characteristics, and they should be designed considering each other. So the inverter has to be designed for the electric machine and electric machine for the inverter, as we will discuss later. The other requirements in the traction application is we want to have a fast dynamic response, so that we can brake, we can accelerate, we can also make sure that the system is capable of taking the corners and so on. So we need to have a dynamic response. We need to account for the frequent starts and stops. In some cases, for example, in a high traffic case, you need to start and stop maybe for hours. We also expect the vehicle is going to operate in the harsh environment, so there will be dust, water, it can get cold, it can get very hot. So for the dust and water, we need to make sure that we have a high IP class, so nothing will enter our drive system. For the cold and hot, we need to make sure that the system can be cooled properly, or it will, for the electric machine and inverter, the cold is not a problem. The cold is going to be problematic for the battery because the battery cannot supply enough current at cold temperatures. And at the moment the inverter and the motor starts running, so anyway, they will get warm quite fast. But they need the cooling. So we want it to have the low frequency service and maintenance. So it is an advantage of electric vehicles compared to the conventional vehicles. You don't need to go for the oil change, or you don't need to have the parts fixed or changed regularly. And we want to keep, of course, this advantage. It should be robust. So you are going to put in on an axle. We talked about the e-axles, and the axles are going to vibrate, they are going to shake, so you are going to hit some places. And so it means that all the connections should be robust and nothing should happen to this drive system. The fault tolerance and safety is super critical because you are going to have passengers on board and the driver on board. So if there is some problem with the drive system, at least we need to understand, and there shouldn't be many safety related issues. So even if there are, so the system should understand it and make sure that the driver knows about it. Okay, so they were the requirements, but actually when you buy a vehicle, so these two are super important. So the comfort and the low cost. So this is what you hear when you drive the vehicle, and the cost is what you pay. So usually you check for the characteristics, the acceleration and the maximum speed and so on, the characteristics that we already talked about. On top of that, you check for the comfort, like the comfort, maybe just not the proper acoustics, but also available space in the vehicle. Available space for the passengers and also for the luggages, for carrying stuff, for other things, let me say like that. So, and also the view is important, as we discussed, so that you cannot very decrease the area, the frontal area and so on. But here very important is the proper acoustics. So we got used to the acoustics of an internal combustion engine, and the frequency spectrum is usually related to the lower frequencies. But on the other hand, when we talk about the electric machines, we are not going to have this low frequency noise, but we are going to have a high frequency noise, because we were talking about internal combustion engines with the motion of the cylinders or the pistons. Of course, we are going to hear a sound, but somehow we are used to that sound. But in the electric machines, electric drives, we are going to hear we may hear the switching of the inverter, and we may hear the vibration of the noise due to the high frequencies happening in the electric machine. And these are annoying. So therefore, even if in decibels it is not high, so we don't like them. So the proper acoustics is a very important criteria for an electric vehicle. And moreover, since we don't have this low frequency, high decibel noise, then all the other noises in the vehicle will be heard by the driver and the passengers. So we need to make sure that also the other parts are not noisy in the vehicle. So of course, the noise will be a problem at low speeds. At high speeds, you will anyway hear lots of wind resistance noise, let's call it like that. And the low cost is another important criteria. So you want to have all the performance, and you want to get it for a low cost. Most of the cost of the vehicle is due to the batteries. So if there is an increase, if the battery technology gets better, the cost of the electric vehicles may decrease. But on the other hand, of course, the cost of the inverter comes in the second place. Then the cost of the electric machine comes, I think, in the third place. So the low cost means that we need to use proper materials. We need to make sure that we don't over-design the system and so on. So actually, it is a very demanding application. So I was looking for some targets. So there's a report by the Department of Energy. So they said that there are some targets for the 2025 passenger vehicles. So these upper ones are for the whole drive system, including the inverter and the electric machine. 33 kilowatts per liter power density, And this corresponds to something around, I was just calculating 480, around something kilometers. So we need to have some 15 years of lifetime. So this lifetime is important because if you design the battery and if you also design the inverter, when you need to decide on the thermal load, then you need to also take care of the lifetime, because the thermal load is going to change the lifetime of the system a lot. So therefore, it is going to be important. And there are also some cost requirements. It is $6 per kilowatt for 100 kilowatt electric traction drivetrain. And it is also required to be highly efficient, compact, reliable, and affordable. And they want to have a building platform for the passenger vehicle. So this is what we talk about, the electric drive unit or the e-axle on Tuesday. So there are also some targets for the inverters. For the cost targets, $2.7 per kilowatts, and for the electric machine, also some power density and also cost targets. So as you see here, that inverter is going to be a little cheaper, it looks like, but I don't know if this is the case already, but they are targets. Here also the inverter cost breakdown. Maybe here you see that the gate driver is the most expensive part, then the power module follows, then the DC capacitor. So these three are the most important components. As you see, this gate driver, power module, then the DC bus capacitor, and of course the control board. So here I just want to mention this DC bus capacitor because we usually don't think that it can be so a big part of the cost. In the inverters, as we are going to discuss later, we need to have a quite big DC bus capacitor to get the less ripple from the PWM and also to be able to supply some reactive power to the electric machine. So it's also getting important. Okay, let's have a break now. I will just stop the recording or pause the recording. Resume the recording. Okay, we have talked about these targets, and Aresh just mentioned that these targets are super tight. We are nowhere close to those values. And it means that if you have a 100 kilowatts system, you want to pay $600 for a 100 kilowatt system. For $600, you can buy a laptop, but you should be able to buy a 100 kilowatts electric traction drive system, I suppose. So it is a tight target. I think we are a little further away from this target. And as we discussed, so there are some increase in the material, so in the cost of the material. So it can be even very tighter compared to the last year. So in the rest of the lecture, I just wanted to discuss with you some commercially available EV and hybrid electric vehicle inverters and also their electric machines. I will start with the inverter, but just keep in mind, actually, we have to use a three-phase inverter because we are using three-phase machines. So if we used a five-phase machine or a DC machine, of course, we would use a different power electronic device, but we use three-phase machines, so that's why we use three-phase. Maybe it's good to write here, three-phase, two-level voltage source inverters. And those inverters are what we have already shown here. So it is a three-phase, it has three legs, and two-level means that at this point, we can have just two different voltages. So either it can go to the DC link or to the zero. If you take the neutral point as here, it can go to the half of the DC link and minus half of the DC link. So these inverters are called two-level voltage source, three-phase inverters. And in all the electric vehicles, the commercially available electric vehicles, we have a three-phase, two-level voltage source inverter. So to be able to prepare this lecture notes, I was using some sources, and they are listed here. So I was using this is maybe, actually, it is better to take it up. I was using some of these, or I deleted some, right? Anyway, let's keep them like that. So, and the results that you are going to see in the tables that you are going to see in the slides are taken from these papers, and both of them are good papers from which you can learn a lot about of the current EVs and hybrid electric vehicles. So this is taken from the first, what I'm going to show is taken from this one, electric drive technology trends, challenges and opportunities. This is not, we're not there yet. It's the electric machine. Okay, it is here. So in this paper, they compared the inverters that we have in the commercial, some of the commercially available EVs and hybrid electric vehicles. And first of all, here it is said that battery electric vehicle, it means it is a pure electric vehicle. So this is hybrid electric vehicle, parallel, I think P stands for the parallel hybrid electric vehicle, the Prius, so which we had to deal with a lot. So I think you kind of know Prius better than all the others. Then we have the Audi. So this is P stands for the plug-in hybrid electric vehicle and battery electric vehicles. So in this case, there are some comments here. So I have copied and pasted from that paper. It's a good paper. So anyway, I will also share the paper. So I think you should read the paper. So first of all of them has a 3-phase 2-level voltage source inverter in all these vehicles to be able to drive the 3-phase AC machines. And all the inverters are built based on silicon-based IGBTs. So at the power level, if we want to use the IGBTs, to be able to use a power switch, we use IGBTs, except for the Tesla Model 3. So this one. Tesla Model 3 is using silicon carbide metal oxide semiconductors. So these are, when it's silicon carbide, they're the MOSFETs. All the others are having the silicon-based IGBTs. Actually, silicon-based IGBTs have a limited switching frequency, and they have you need some thermal constraints. But on the other hand, they are highly available on the market and their cost is very competitive. So therefore, in most of the electric vehicles, we use that technology instead of the wide bandgap devices. So in all the designs, we have IGBT module. IGBT module means that we are to carry all the current in a phase, we are going to have a big switch, IGBT switch, and which is going to be a module level. But on the other hand, in Tesla Model S, this 70D, 70 means what does it mean? Do you remember? What is the 70D means? Any idea? What can be D?
Sport or normal, something like that.
D is all-wheel drive.
Um,
Double, I think, stands for double. What's 70? You don't need to know, you can guess.
Battery energy, maybe.
Exactly, 70 kilowatt hours. So it means that the system has a 70 kilowatt of hours of battery, and it is double drive, so front and rear drive. So they have different names like that. And in the Tesla Model S, they used 36 of T0 to 47 discrete IGBTs. So instead of using a one IGBT module, which can carry high current by its own, and then you need just 6 of these modules for inverter. So this is going to be one module, another module. Actually, they can be also in the single packaging. So one leg can be in a single packaging. So instead of using those modules, so they have used instead of one switch, 36 parallel discrete IGBTs. Why they need 36 of them? How they can decide on the value of 36?
maximum current.
Exactly. So this IGBT modules can carry a high current, but this TO247 most probably cannot carry such a high current. Maybe they can carry some current around 10 amps or 20 amps. So to be able to increase the current capability of the inverter, instead of using one big IGBT module, they make many small IGBT modules, IGBTs parallel to each other. So actually it sounds easy to put all these things parallel, but actually it is very dangerous, because if you cannot turn them at the same time on and turn them at the same time off, so it means that they can have a very unbalanced current on them and they may fail. So actually it is not a very easy stuff. Okay, the other takeaway message is all of them has a DC link voltage around 400 volts. So 350, 430, or 300 to 400, because we learned that actually the battery voltage is not going to be constant. Depending on the SOC, the battery voltage is going to fluctuate anyway. But so that's why it is maybe enough just to write here a value around 400 volts. Just except for the Pirius. Why the Pirius has 600 volts? What do you remember regarding the Pirius? There was some additional components. Actually, it is also written here. Okay, I don't need to ask. So just the Pirius has around 600 volts, and actually it is battery voltage was around 200 something volts as far as I remember, and they were just using a DC-DC boost converter to have a higher voltage at the machine terminals or at the inverter terminals. But this is not very common. We don't have many vehicles with an additional DC-DC boost stage, because I think it adds to the cost. It makes the system more complicated. And that's why they learned how to deal with the fluctuating DC link voltages in terms of the electric machine control. And here, this is important. Another important thing is the maximum switching frequency, which was written somewhere here on 1200 hertz or 1.2 kilohertz. So here what you, or this is fundamental frequency, I'm sorry, the maximum fundamental frequency. So this is not the switching frequency. Their switching frequencies are not shown here. So the maximum fundamental frequency is related to the frequency of the created AC currents. And this frequency is going to be based on the electric machine speed and max plus pole pair number. Pole pair number. Pole pair number. So for example, if we have, maybe let's calculate one of those fundamental frequencies. If we have the maximum speed of 15,000 RPM, and if we have an electric machine with pole number equal to 8, so this means that pole pairs is going to be 4. So what is the maximum fundamental frequency of this drive system? How do I calculate it? And max, so this is the maximum frequency, maximum speed. I want to get the fundamental frequency, the maximum fundamental frequency, and the maximum fundamental frequency is going to happen at the maximum speed, and assume that we do it for a synchronous machine. For an induction machine, it may be, so there will be a slip factor, but anyway, it's not going to affect much. So if I give you such a drive system, how do you calculate the fundamental frequency? The highest fundamental frequency? Okay, you can do it. You can wake up. No one?
N equals 120F over pole pairs.
Okay, so tell me with those numbers. Don't tell me the equation. Tell me the
value. You want to?
I want to use these values here. So what is that? 15,000 RPM. So this is the
60'a bölersek hertz oluyor. Nmax
500.
Okay, so this is in 1/seconds, right? This is hertz. Okay. And what is this value?
Bu Nmax rotorunki herhalde. Yani wheel'ın Nmax'ını söylemediniz. Rotorunkini söylediysek.
Yeah.
O zaman bu rotorunki elektrik frekansını çevirmek istiyorsak da 4 ile çarpacağız.
So that this will be the electrical frequency. So 15,000 RPM means that our shaft is going to rotate 15,000 times per minute, 15,000 turns per minute. This is what we see from the shaft of the electric machine. So it means that it is going, of course, we need to calculate the frequency over 1/second. We cannot use the minute value. So we need to divide it by 60 so that we can get the mechanical frequency in 1/seconds. So which is the definition of the hertz. Oops, in the morning, they shouldn't wake me up. Anyway, hertz. And we need to multiply it by 4 because as the shaft rotates 1, the magnetic field in our electric machine is going to rotate it 4 times. So because here in a 8-pole machine, we are going to have 1 circulation here, another here, another here, and another here. We are going to have in total 4 north poles. So for example, this is one of the north poles, and 4 south poles. So therefore, we need to also multiply it by 4 to get the electrical frequency. And what is this value? I think Aresh has calculated it.
500.
1,000, right? I calculated 1,000. 15 divided by 60 times 4. It is 1,000. So this is 1,000 hertz. So this 1,000 hertz is the frequency of the rotor field. And this is a synchronous machine. This should be, so this is the frequency of, due to the rotation of the rotor field. And this should correspond, so frequency of the rotor field due to rotation. And of course, this is a synchronous machine, which has to be same as the stator frequency. Stator frequency should be same as the rotor frequency. Rotor currents has a frequency of 0. Rotor has DC currents, but it has a rotor frequency because of the rotation. Anyway, so I think you all know these. So the stator frequency has to be 1,000 hertz. And in this table, what is put here, this F1, is basically this value. So the maximum speed of the vehicle divided by 60, because it is given in RPM, multiplied by the pole pair number. And what you can see is these maximum frequencies are all below 1,200 hertz. Actually, they are usually below 1,000 hertz. What is limiting? Why we don't have a maximum frequency of 2,000 hertz? You know, we can just increase the pole pair number. We can just increase the speed. Why do you limit ourselves around 1,000 hertz maximum fundamental frequency? Any idea?
Are you asking from the point of electric machine or inverter?
I'm asking in terms of inverters. Later, I will ask regarding the electric machines.
Okay, yeah, higher switching frequency means higher losses, I guess.
Okay.
Related to the
so what happens if you exactly? So if you increase the frequency, then you mean that you need to have a different technology for the power switches, right? And as you increase the frequency, so it means that if your stator current is going to change with, so assume that this is your stator voltage, the fundamental of your stator voltage. and it has a frequency of 1000 Hertz, just for sake of an example. So this is VA, some voltage of the stage. And you want to apply a PWM, pulse width modulation. So what should be the switching frequency regarding to the pulse width modulation? Can you just decide on a switching frequency for 1000 Hertz fundamental? Come on, you know it, so just say it. Huh?
2000.
How much again?
20.
10 times.
20.
20 times of fundamental.
Okay, so there is a rule in power electronics, as Ogun said, 21 times. So, right, you learn something like that.
Yes.
21 times of the maximum frequency. But the problem with the variable speed drives is actually frequency is going to change all the time. So this is 1000 Hertz at 15,000 RPM. What about at 1500 RPM? Right, so this is at 1000 Hertz as this much. And if you have 1500 RPM, then you, of course, you are going to have something which I cannot draw. So it is going to be 100 Hertz at 1500 RPM, right? It's going to be 10 times less. So it means that actually it would be great if we can design the system with 21 times higher switching frequency. But the problem is we cannot keep this a value constant because our frequency of the fundamental is going to change with the speed. So there is a rule to make sure that the system is still controllable at its maximum speed. We need to have switching frequency around, it is not a perfect rule, 10 times of the fundamental frequency, maximum fundamental frequency. So it means that here, if I have one kilohertz, then my switching frequency of the inverter should be around 10 kilohertz. So for F1 max is 1 kilohertz, then Fs should be around 10 kilohertz. Because actually, if you want to keep this 20 ratio, here you need to have a very fast switch. So there is a big trade-off. And on the other hand, we know that the machine is just going to operate for a short term at this RPM. In most of the cases, it is going to operate at the lower speed, at the 1500 RPM or 3000 RPM. So actually, you don't need such a high ratio with respect to the high speed, but you need to still make sure that your system is controllable. And this 10 means that at the highest frequency, you are going to have 10 times PWM signals. So even this is too much. As you see, it is very few points. So actually 20 makes sense, but it will be a very over design for the low speed. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. So you are going to just apply PWM at these signals. So there is a rule like it should be around 10 with respect to the highest frequency. So it says that actually, if you want to keep the fundamental frequency around 800 or 1000, it means that they keep the switching frequency around 10K or 12K. And maybe you remember here, they said that we can use silicon-based IGBTs. And as you know, the silicon-based IGBTs are not known for their fast turn on and turn off times. So it means that actually the used technology, the silicon-based IGBTs, are going to limit our maximum frequency, and so it's a switching frequency, so the maximum frequency. And here, as you see, the maximum fundamental frequency is limited by the maximum inverter PWM switching frequency. And this maximum PWM switching frequency is limited due to the IGBTs that we are using. And as this motor gets faster, or as the pole pair number gets more, or as both their multiplication increases, then we may need to use inverter with a higher switching frequency. But for now, if you use the silicon-based IGBTs, you need to make sure that you have a limited maximum speed and limited pole number. So the rule is, the 21 rule is correct for the constant frequency applications, because the fundamental is going to be the same. For example, if you always have a 50 hertz output, then you will say multiplied by 21. But in this case, it will be too much, because we are not going to operate at the maximum speed for a long time. So there is a rule like around 10. It should be at least around 10. So therefore, actually, we need to make sure that the frequencies are not going beyond 2200 hertz, most probably because of the IGBTs. With the IGBTs, we can have a maximum switching frequency around 12,000 hertz. Why the switching frequency of the IGBTs are limited? What is limiting the switching frequency of the IGBT?
Kapasitesi olabilir mi? Yani
Okay,
CHP.
so yeah, what is wrong with that capacitance? Do you want to have it small or big?
I want to have it small.
Okay, so Mehmet says that actually because of the gate capacitance, the IGBTs will take longer time to turn on. And also then after that, they also need longer time to turn off. And the switching frequency is related to the turn on times of the devices. If they cannot turn on fast, it means that you cannot switch fast. So therefore it is limited. And actually this brings us to the next part, so the trends in the inverter. So first of all, we learned that we usually have three-phase voltage source inverter, two-level voltage source inverter. Two-level is used because it is compact, it has the minimum number of the switches, and it is easy to control. And most probably, we will keep on having the two-level inverter for a while. When we want, what we ask from the inverter is we want it to even get more compact, and it will be only possible with the system integration, so that it has to be integrated with the electric machine, and also the cooling has to get better. So we need to design the cooling better so that it can get even more compact. And another trend is the use of wide bandgap devices. So these wide bandgap devices are the GaN devices and also silicon carbide devices. So the wide bandgap devices can give us two possibilities. The first one is the higher frequency. They can turn on and turn off faster than the silicon-based IGBTs. And second of all, they can, with those devices, a higher junction temperature can be allowed. So for the silicon, the junction temperature should be limited around 120 degrees, but for the wide gap devices, they can have a higher junction temperature, but still, of course, the packaging should also different. So if the packaging can allow, you can make use of this higher possible junction temperature allowed by the wide bandgap devices. So when it comes to wide bandgap devices, there are lots of research on the use of them. So the silicon carbide modules are available at different voltage levels and power levels. Silicon carbides, but the GaN devices are limited in terms of the voltage levels. But there's research going on the wide bandgap devices. On the other hand, if you use a wide bandgap device, the problem is going to be the DVDTs in our drive system. With the wide bandgap devices, DVDTs are going to increase. So these DVDTs are related to the turn-on times of the PVM, of the switches. So if the switches can turn on fast, it means that the inverter voltage is going to increase fast and during the switchings, and also the electric machine is going to see a high DVDT. So these high DVDTs are bad for the stray inductances and stray capacitances in the system. And it is also bad for the electric machine. Why is it bad for the electric machine? What is wrong with dV/dt to the electric machine? Who cares what dV/dt does the electric machine see?
Maybe it could affect our wires, copper, insulation.
Insulation. So insulation is designed for a given voltage level, but as the dV/dt increases, so there will be problems with the insulation. There will be insulation damage, and there will be some capacitive effects between the insulation and stator. So we have a new professor working on that in our department, by the way. Actually, it is good to have wide bandgap devices because it will allow us to go to the higher frequencies, and it will allow us to make a system smaller. But on the other hand, we need to also make sure that this dV/dt is not causing some waves and electromagnetic interference in our system. And so there will be really some, how they call it? Anyway, so due to these high frequencies, our electric currents are going to behave like waves in the circuit, and there will be some yansıyan. I don't know. Maybe let me check and tell you about the name. I cannot remember the terminology. So that's why we also need to make sure that this dV/dt can be handled in the drive system. Moreover, the insulation of EM is not damaged. So there will be a problem with the insulations of the electric machines. The other trend is the use of the higher DC link voltages. Currently, almost all the vehicles have a DC link voltage levels around 400 volts. And now there's a trend to have a higher voltage range, a higher voltage around 800 volts. So the 800 volt is going to be good for the inverter because then the inverter rating current is going to decrease. Of course, it is voltage rating has to increase. So we need to have the devices with the higher voltage rating. And as the voltage increases, it will be good in terms of the current rating. Current rating of the inverter will decrease, and the current rating of the electric machine will decrease, so that actually the electric machine gets more compact. More current means more copper, and more copper means a bigger electric machine. So that if we can increase the DC link voltage, the electric machine is going to get smaller. But of course, there is a limit. We also need to think about the insulation, so insulating materials, and so on. And recently, we also found out that these higher DC link voltages are good for the fast charging, because then the currents can decrease for the same power region. So, okay, before we continue, why do we have 400 volts? Is it by luck? Why do all of them choose a 400 volt DC link voltage?
Rectified line voltage.
Okay, so Ogun, where is the line in our system? It is related to that, but not exactly. So it is not directly related, indirectly related.
Safety
Other
issues,
part, charging.
regulations.
But we are talking about the inverter.
Okay.
About that. So it is related somehow, Ogun. It will come to that, but we don't have the line.
I think
Wasn't it related to the voltage of IGBTs?
Exactly. So what is the voltage rating of our available IGBTs on the market?
650, something like that.
IGBT ratings. Perfect. So there are ratings with 600 to 650 volts, or now I think there are 700 to 750 volt ratings too. And what the next rating is the 1200 volts. So if you use a two-level inverter, we will talk about it later. Two-level inverter. So this is my two-level inverter. You will get used to that, my two-level inverters. So this is going to be, I am going to have the DC link capacitor. It is important. So if I have here 400 volts, it means that one of the device, if for example, this is the conduction pad and something like that is coming. Then one of the device has to be able to block the 400 volts. So the volt, so if they are conducting, it doesn't block any voltage, of course, but if it is not conducting, it has to block the 400 volts. And some of you was talking about some safety. What was the content of this comment?
Yeah, I was meant that inside I was talking about the safety to the human more.
Arash, 400 volt and 800 volt, they are both dangerous. They kill you, both of them, no worries.
Okay.
So it is for sure that you will die from both of them. The safety, maybe the safety margin is actually here. If you use a 650 volts of silicon IGBT, you cannot put here a 600 volt DC link voltage, because DC link voltage is not going to be stable. It is going to oscillate. So therefore you want to put a margin. And like then, for example, with that kind of a IGBT, you will allow it to be 400 volts. With 750 volt IGBT, you will allow it to be 500 volts maximum. So therefore, actually, this 400 range selection was due to the available IGBTs, silicon IGBTs. So if we want to go to the 800 volt, then we need to use this 1200 volt IGBTs, 1200 volt rated IGBTs or MOSFETs has to be used to be able to go to the higher voltages. So therefore, if you want to use the commonly available IGBTs, then you have to stay somewhere around 400 volts. Okay, so, and Ogun, why do we have the IGBT, so common IGBTs have the 600 volt rating, not the 300 volt rating?
Of the rectifiers this time.
Exactly, because, you know, if you want to decide on the rating of an IGBT, so it could be 500, it could be 300, it could be 800, but I feel like, I'm not an expert on this topic, but I feel like they have to decide on this value, the 600 volt or 650 volts, so that we can use it in line connected systems. Because in the line connected systems, the DC link voltages are going to be around 400 volts or 5 or even 600 volts, right? Depends on the connection. But it should be, I think it is related to that. This is my guess. I'm, as I said, I'm not an expert on this topic, but there should be a correlation between that. This is what I feel. So it means that 400 volt was not by luck, so it was due to the available technology. You are going to see, if you are working on application, you need to follow the available technology, and you need to also ask more from the available technology. So the technology is getting better in the direction that you want it to be. And in this case, for example, the GaN transistors are not available in the 1200 volt range. So it means that this 800 volt cannot be realized with GaN for now, but maybe in future it will change. So higher DC link voltages, lower currents, which is good. And it is also good for the faster charging. So these are the trends in the inverter technology. And now, do you have any comments or any questions regarding to that? Okay, let me continue with the electric machine types too. Otherwise, we cannot finish the topics again. So we said that we have usually three-phase AC machines, and due to this three-phase AC machines, we need to have a three-phase inverter, and usually we use a three-phase two-level voltage source inverter with silicon IGBTs up to 10,000, 1,000, or 12,000 fundamental frequency control applications. Then the machines that we use in the electric vehicles are also very specific. There are some trends, the types of the electric machines are changing, but for now, we usually see one type of electric machine. So let me tell you the end of the story so that you listen carefully. So here we usually have this type of machines, IPMSM, interior permanent magnet synchronous machines in almost all the vehicles, except for a few vehicles, which of them are using the induction machines. Actually, we have more machine types available. When we talk about the electric machines, we can divide them as the synchronous machines and the asynchronous machines. Moreover, rotating field machines, switched field machines, or DC field machines, and so on. So first of all the vehicles are using a three-phase system because the three-phase system is compact and it is with less components. We could also use a five-phase system, but to increase the number of devices or number of legs, number of phases doesn't bring much, at least in a small power applications. For a 100 kilowatt machine, three phase is good enough. But if you go to the higher values of the power, like in the megawatt range, you may need to have multiple phases so that your power electronic devices can be smaller. But in the electric machines in the electric vehicles, usually three phase is good because we don't need to divide the power electronic units into smaller groups. And if we increase the number of phases, then the complexity of the system due to the connections is going to increase. So therefore, we always use a three-phase machines, and this is the most common number of phases for the electric machines. Anyway, it is also related that we have a three-phase system, but yeah, but of course in the vehicle we don't have the three-phase power system, so therefore we could have any number of phases, but still three is good enough. We don't gain much if we increase the phase number to 5 at this power level. So we usually use synchronous machines. As I said, this machine is used in most of the electric vehicles. Interior permanent magnet synchronous machine is used in most of the electric vehicles, and in few of them we are using induction machine. So first of all, this interior permanent magnet synchronous machines and induction machines, they have the same stator. I'm going to share the lecture notes to explain you the rotating field again in this created by the stator. So all of the machines have the same stator. The stator is a three-phase stator with rotating field. So we are creating a rotating field. And their rotors are different. So these ones are the permanent magnets with the colors. Each color shows a different orientation. And so this is the surface mount permanent magnet machine. This is interior permanent magnet synchronous machine. And this is the induction machine. And an induction machine, so as you know, all these coppers, rotor coppers, are short-circuited, so that they are all brushless machines. So you don't need any brushes to the rotor. Here you have just permanent magnets in the rotor. Here you have the short-circuited copper or aluminum conductors in the rotor. So in this case, the difference, they are going to be different. Here the magnets are on the surface. Here the magnets are inside. So this is the main difference between these two machines. And we also have other machine types. For example, here we had only the magnetic force. So there were just magnets, and the stator field and the magnet field was interacting. So we had just that force. Also here, we are going to have an induced field in the rotor. This is going to interact with the stator field so that we are going to have a rotation. But once we put the magnets inside, we are going to also have some reluctance effect, because the reluctance seen from this axis and the reluctance in this axis is going to be different. So it means that even if I remove the magnets here, and if I supply some rotating field in the stator, then the rotor will tend to rotate, just because to decrease the reluctance. So maybe you remember it from the other courses or from 361, we talk about something like that. So if this piece is able to rotate, able to move, and if we supply some current to this winding, what we know is the system will try to reduce the reluctance, and there's going to be force in that direction. So it means that since the system has lower reluctance in this direction will try to align itself with the stator field. So even if you remove the magnets in this case from here, just get rid of the magnets, the system will try to, the rotor will try to align with the rotating magnetic field. So we still expect a rotation. But in this case, if you remove the magnets, the reluctance in the Q direction and reluctance in the D direction are just going to be the same, so that we don't expect to have any reluctance torque. Same thing here. So here we have also some reluctance effect. So like, let's say mutual torque plus reluctance torque. And in this case, we are just going to have the mutual torque. And here we are going to have the mutual torque, only mutual torque. Mutual torque, I mean the mutual interact due to the interaction of the rotor field and the stator field. This reluctance torque is due to only the stator field. Rotor is just operating as a magnetic piece. So, and there are also other types of magnets. So if you, as I said, if you just remove the magnets, it will also create some reluctance. So this is the synchronous reluctance machine. This is just going to have the reluctance torque, because there is no magnet, no field in the rotor that can interact with the stator. So there can be just reluctance torque. Here you can just put some few magnets in this openings here. And here you are going to have a high reluctance torque and a low mutual torque. Actually, this middle configuration is very similar to the middle configuration here, but in this case, you have more magnets, less reluctance torque. Here you have more reluctance torque and less magnets. This is the basic difference. And the last one is the switch reluctance machine. Switch reluctance machine operation is also just on the reluctance torque, as the name suggests, as you see here. And it is just, we are going to have just reluctance torque, because as you see in the rotor, there are no windings, but just a reluctance change. For example, if you supply some positive current to the phase B, this pole piece will try to rotate in that direction. Or if you supply a positive current into the C, it will try to rotate in the other direction. This is exactly this kind of a force that we define. So from all these machines, this the first three and these two have the same stator, which is a three-phase stator. And this one has a switch reluctance machine type of a stator. So this has a different stator. And this will need a different inverter. So the inverter topology that we have discussed can be used the first 5 of the machines, but not for this machine. This will require a different inverter is required, because it is going to have a different control, and it can also have multiple, more than 3 phases, but also 3-phase systems is very similar. So when we compare all, and I just put here the machines with 4 poles, but as we are going to see, actually, usually in the drive system, the machines do have higher pole numbers than 4. And when we compare these machines, and if we check them in terms of, for example, torque, power density, DC link utilization, field weakening, this external speed range, power factor, efficiency, torque ripple, and other values. Actually, one thing that we see is IPMSM is quite advantageous in terms of the torque, power density, efficiency, and power factor. So IPMSM is this configuration, interior permanent magnet synchronous machine, where we have both the mutual torque and the reluctance torque. Moreover, it has some problems in terms of the fault tolerance. It is one of the insight of these ones. The fault tolerance of the permanent magnet machines are low, because even if you don't supply any stator current, there will be some magnet rotating in the rotor, and this rotation is going to cause some induced voltage. And this induced voltage can be dangerous in some types of the inverter faults or rotor faults. And there are also the other types. But as I said, for the electric machines, electric vehicles, we use IPMSM because of its high torque and power density and the efficiency. So this is the reason why we use it. Moreover, it also has a good power factor. Power factor is not a big deal for the electric machine, but it is a big deal for the inverter, because when you size your inverter, you need to size it for the volt amperes, not for the real power, so that if the system has a low power factor, it means if the machine has a low power factor, it means that you need a bigger inverter. The current rating and voltage rating of the inverter is going to increase if you have a bad power factor. So due to these facts, IPMSM, torque density, efficiency, and power factor is highly used in most of the vehicles. And induction machine is also the other option, as we are going to discuss. So maybe one question can be, why do we use IPMSM but not surface mount? There is not much difference between them. So the answer is actually they have a big difference when it comes to the high speed performance. So we will also talk about it in this lecture, but in this introduction part, I also want to show you some results. So the interior permanent magnet machine, so this is torque speed characteristics. This is what we have defined already. This is say constant power speed ratio. So the interior permanent magnet machines can reach a constant power speed ratio around 5. So which is very good. Actually, it should be around 3.5 to 4 is even a good design. So 5 is a very good design, but at least it can reach a high value. On the other hand, the surface mount motor, which was this SM surface mounted motor, this is the first one. Let's maybe call them the first one, is going to have these characteristics. And this says that actually it can give you high torque, but it cannot keep this torque for a long time. So therefore, we don't use the surface mounted permanent magnet machines as the drive system motors because they don't have a very high speed ratio, the Nmax to Nc ratio. And the same thing happens for the brushless DC machines. Actually, brushless DC machines are the surface mount permanent magnet machines. And therefore, we don't see any of the surface mounted permanent magnet machines in drive system applications. This is also the characteristics of the asynchronous machines, which is already, actually this can be a little higher, times two times. You can reach maybe 2 times. With the synchronous machines, 2.7 is a good value. It is what you can use. So it means that when selecting a electric machine, you also need to consider its torque speed characteristics. And this is where the surface mounted permanent magnet machines are losing the game and where the IPMSM is winning. And when we compare also these two designs, there is also one very important difference in terms of the mechanical stability of the magnets. Here, the magnets are glued to the surface of the rotor, so its production is easy. But of course, with the high centrifugal forces, the magnets are going to see a high force. So these glues cannot hold them. So we need to put some bandages around the magnet, so the magnets stay around the rotor even at high speeds. And in this case, the bandages are getting expensive, and they also have a limit, and so on. Therefore, these IPMSMs are also good for the high-speed operation in terms of the mechanical robustness, because since the magnets are inside the rotor, they cannot fly out. Here, the magnets can fly out. So therefore, the IPMSMs are also better compared to the, so these are better in terms of better mechanical robustness plus better how do we call it? CPSR. CPSR. So therefore, we use interior permanent magnet machines. in the commercially available EVs. And the IPMSMs are the choice in 90% of the electric vehicles so far because of their high power and torque density and because of their high efficiency. Because of their high torque and power density and efficiency, we can really pack them in the compact way and we can place them in the electric vehicles. And it is also easier to cool because we just need to cool the stator, or it will be enough if we just cool the stator because of the absence of the rotor copper loss. So this is the type of the electric machine we have in almost all the electric vehicles. Since the stators are same, in next time I will also talk about how the rotors look like of the IPMSMs. But the rotor can be different, but mainly there are some V-shape or U-shape or W, V shapes, and the magnets are going to be inside. Anyway, we can talk about them later. And the reason why some electric vehicles, which electric vehicles have induction machines? Any idea? It comes in the next slides, but I just want to ask.
Some versions of Tesla, initial version.
Some versions of Tesla. I think Renault used to have some induction machines earlier.
Yes, I think Renault Zoe also have induction. I'm not sure.
One of them used to have induction machines. I don't know the current situation. And some Audi models have induction machines, and all the rest has IPMSM machines. We will also talk about the trends. It may change in the near future. But what is the use of induction machines? Basically, the absence of the permanent magnets. They don't want to rely on the permanent magnet prices. Makes the induction machines interesting. But of course, the induction machines have a lower torque density and power density. One very interesting characteristics of the induction machine is the fact that there are no magnets, so nothing can demagnetize. And it means that for a shorter times, you can allow high temperatures. I think it should be here. Higher peak stator current because of the thermal actually. So thermally, they can get hot. They are allowed to get hot because these PM machines, they are not allowed to get hot. So if they got hot too much, then their magnets can be demagnetized. But on the other hand, an induction machine, so the rotor temperature must be limited so that this for PMs not to demagnetize. But here we don't have such a problem. Here is had a problem. So the induction machines are good for overload capability. We call it overload capability. So the difference between the continuous operation and the short-term operation. So these induction machines can give you very high torque for just short durations because we can let the system to get hot without any risking any demagnetization. So that's why the induction machines can be handy. Because of the absence of the permanent magnets, their costs are stable and they don't have high cogging torque. And moreover, maybe I should also write here, in terms of the fault tolerance or safety, their induction machines are better. Fault tolerance. Because here we have already always a permanent magnet which is rotating. But here, if you don't supply any current to the stator, there won't be any induced voltage. It means that if you don't energize the stator, you won't get any induced voltage. No EMF when stator is not energized. But in this case, even if you don't supply any current to the stator, you will have a rotating field. And due to this rotating field in the rotor, rotor field, there you will have some induced voltages in the stator terminals. And this can get dangerous in some cases because the inverter is going to always see some voltage. Here, you can just shut down the electric machine and there won't be any induced voltage in the system. So therefore, also induction machines are better. Okay, let us stop here. We will talk about the types of the electric machines that we have in the electric vehicles. We will talk about the trends, the number of poles, number of maximum speed, and power and torque values, their winding types, their cooling types, and so on. We will just talk about the trends. I think we can do it on next Tuesday and just finish this topic on Tuesday. Okay, so let me